Assalamu alaikum. So this is our continuation on the mechanism machine lectures, and for this presentation we will talk about the position analysis. So such analysis is important in mechanisms because when you want to find out further categories like the velocity, acceleration of the mechanism, before that we need to know where exactly the position of the different links. So for example, you have been given one certain position of one of the link and you will be asked to determine position of other links. So that's what we will learn from this presentation. Again, why we need it? Because this would require further on when you want to find out how the velocity, each link is doing its velocity and its acceleration subsequently. So starting with a little bit of basic, and then we will just slowly cover the complex topic actually. So location, for example, this is one of the diagrams shown. So P is located x units along x-axis. So let's say you have this x, y, z Cartesian coordinates. This is x, this is y, and this is z. And P point is in space, like it's three-dimensionally. And when it says, so it is actually x distance far from origin, y distance far from origin, and of course the z position far from the origin basically. So that's what it says. The P point located x units along the x-axis, y units along the y-axis, and z units along the z-axis. Three vitally important parts of definition depend on the existence of reference coordinate system. So whenever you want to show that this is specific particular location of a point, first you need to define what is your reference coordinate system basically. So the origin O of coordinate system provides an agreed upon location from which to measure the location of point P. So for example, in this one, this O is the reference region for the Cartesian coordinate system, which we meant to measure. The coordinate axes provide agreed upon direction. So the axis, the x, y, z axis, agreed upon directions along which the measurement are to be made. They also provide known lines and planes for the definition and measurement of angles. The unit distance along any of the axes provide a scale of quantifying distance. So this is like three procedures. One, you need to define what is the origin. Second, what is the length, what direction of the length for each subsequent axis. And third, how far it is. So y in terms of magnitude will give you what is the length we are covering basically. All right, so now this is a locus of moving point. So this is again like providing the opportunity to identify where the point is located. So the observations are not restricted to Cartesian. So now this Cartesian coordinates which we have used x, y, z, it's not necessary that you always use that for any point to locate the point. So all three properties of coordinate system are also necessary in defining cylindric coordinates. So for example, you can do in cylindrical coordinates, you know that cylindrical coordinates can be represented by two lengths, two linear dimensions and one angular, or you have spheric conditions where you have one radius and two angles. I'm quite sure you are familiar with such coordinate systems in different subjects. So, or any other coordinate of point P. So it could be any other thing. The same properties are also required if point P is restricted to remain in a single plane and a two-dimensional coordinate system is used. So the point, the P point, when we are talking about the point, basically it will restrict to be restrained at one specific location. No matter how it is defined, the concept of the position of a point cannot be realized without the definition of reference coordinate system. This is true. So without coordinate system, you can never ever explain where the point lies actually. So the direction cosine for locating point P. So one of the trigonometric way, analytical ways to define the direction is using the direction cosine. Direction cosine is basically cos of angles. So for example, cos alpha is basically x over r, cos beta y over r. R is basically the distance from the origin, and cos gamma is a z over r. Yeah. So now what is alpha, beta, gamma here? So three angles. So alpha, beta, gamma are the angles measured from the positive. So you need to mention this actually, because the coordinate system works like that. So the alpha, beta, gamma are measured from positive x, positive y, and positive z direction coordinates. So x coordinate axis to the directed line of OP. So for example, you got three-dimensional. So direction cosine you might have seen somewhere already. So for example, this is the P basically, which is distance r from origin. This is P, and let's say this is x, this is y, this is z. So I would just write for x, for example, it is x distance from center, from the origin, this point. So you can just find out the direction cosine, which is the alpha. So alpha, the cos alpha would be, if this is alpha, so cos alpha would be x over r. So yeah, so the base and over hypotenuse. So you can do for each individual angle basically. One means of expressing the motion of a point or particle is to define its component along the reference axis as function of some parameters such as time. Now we have some additional complexity here, is the addition of time as a variable. So you got already Cartesian coordinates where you have x, y, z. Now if they are moving, so of course we will have some time contribution as well. So in that case, you normally represent it like that. So x is as a x function of time, y as a y function of time, z as a z. When the time changes, so the orientation will change. So this is one of the example, very basic example actually. So describe the motion of a particle P. 2.1 problem example solved in a book. So a particle motion whose position changes with time according to this equation. So the x location is changing through this equation, y location is changing through this location, and z location is changing because of this one. So you see each x, y, z is being related with the time. So if the time is changing, so then the particle, for example, in 1 second of time, the particle has covered this much distance, which can be measured with this equation. And during that same 1 second, the y orientation has changed to this one, and z orientation has changed to this one. So now he's asking here, describe the motion of a particle whose position changes. So now, because three set of equations are defining the particle, so that's why we need to find out how the particle literally is moving with reference to Cartesian coordinate system, because we are talking about x, y, z. So now what you do, substitute values for t from 0 to 2. So we are just doing for 2 seconds. Yeah. Let's say if in problem is not mentioning that how you have to go to 2 seconds, 5 seconds, but you can try to establish such time where you have enough data to produce what the graph will look like basically. So here 2 seconds is reasonable number, and that gives the coordinate listed in table 2.1. So now this is table 2.1, where what you have done, you change time from 0 to 2 seconds, but each one is divided in 8 equal numbers basically. So 0, 1 by 4 second, 1 by 2 second, 3 by 4, 1. So like quarter of second we are moving basically. And then what you do, you just plug this time within the equation. So x is equal to a cos 2 pi t. So x is equal to 2. So you plug in the number. So when you can just see cos 2 pi t, when I plug t is equal to 0, so it is cos 0. Cos 0 is 1. So that's why I'm getting a. When I'm on another equation, y is equal to a sine 2 pi t. When I plug in t is equal to 0, so sine 2 pi 0, or sine 0 is 0, so that's why we have a 0. So, and then z is because it doesn't have any cos or sine, so it's just like dt. So with the 0 time, it will be 0. So this is one way. Same way you can do for 1 by 4, the next step increment, and you will find that at x is equal to 0, you are getting 0. So when we have basically y is equal to so you plug in t is equal to 1 by 4, so you will have y, and then z as well. So as shown in figure 2.2, the particle moves. So now we want to find out how these parameters. So we have determined x, y, z for all range of times. So from starting from 0 and going towards 2. So you have already found all the locations which is given over here. Now it's time to see or plot how different positions on the Cartesian coordinate system. So what is it basically? You have if you see carefully what it says is explains there. It's shown in figure 2.2, which is this one, the figure, this one. The particle moves with a helical motion with radius a. So you see the x direction shows a helical basically. So at 0 we have a, at 1 by 4 we got 0, then it's a minus a, then 0, then a, then 0, then minus a, 0 a. So it is definitely moving with the radius of a basically around the z axis with a lead of b, and it goes opposite. So for example, here we have a, here we have 0. When it says 0, this is a. When it says minus a, this is 0, then 0 is a. So basically it is kind of like moving a circle, basically making a circle. If you just look at x and y, so x and y shows a this particle moving just in a circle basically, but the z is contributing here. So z is causing the particle to move each time b by 4 ahead. So b by 4 plus b by 4 is a b by 2. B by 2 plus b by 4 is a 3b by 4, and 3b by 4 plus b by 4 is a b. So the particle, if you just look at x and y, just wants to move in a circle. When if something is moving in a circle and also covering some distance, in that case it's more like a helix basically. So this is a helical motion. And how faster is going in z direction is the lead of b basically, right? Because within 1 second from here to here, the particle already covered b distance, right? And in the 2 seconds it will cover another another b. So that's what he's saying. The z-axis with a lead of b. Note that if b is equal to 0, then z is equal to 0. So when b is equal to 0, so we are at this position. So we start from here. The moving particle is confined to xy plane and the motion is circle with its center at origin. That's what I explained. If let's say this equation z is equal to b, instead of bt we have 0. So this is just a circle actually, the particle moving in a circle, right? So this is the way we explain the movement of a point, which helps you to understand what kind of motions we expect from this system basically. All right, so there is a next problem. uh, I'm just providing you the solution as well. So this is a problem 2.1 because this looks quite similar to the one we have done. So I just leave it to you to calculate. um, I'm quite sure you will not find it any difficulty. There is a little bit of different nomenclature being used. For example, here you had like x is equal to a cos 2 pi t, but instead of that you are writing it RA basically. So RA is equal to AT cos 2 pi t. So of course what you will do, you will find out different positions, uh, changing this time. Instead of you can plug in time from 0 to onwards, and you can decide what locations, what increment you have to select. So nevertheless you can conclude RA to RAX, this represents the X movement, RY is the Y direction, and RZ is 0. So this is a little bit simpler. So of course it's not like a helical, uh, like a helix, the one it moves in Z direction, but rather it is like that the when it's shown the answer basically. So for you it would be to find out what the best way to use time, what time you use, and once you know that, you can just plug in to find out what will be the x by calculating from this equation, and what will be the y because of this one, and z is basically 0. So this is like rax, and this is ray basically, or ray y basically, and this is z basically. So this will be 0, all 0 basically. So then you have to choose what best suitable time you have to use basically. So you construct this table, and from the table you can then show that how this helix will be formed. All right. So again, a little bit of more nomenclature for the position analysis. So the position of a point as the vector form from the origin of a specified reference coordinate system to the point. So the position basically we define from the reference coordinate system. Now it is convenient to express the position vector in terms of components along the coordinate axis. So that's the one of the way to represent a vector basically. So for example, this one, the diagram is quite nice diagram where you it's been shown as a unit vectors. So for example, you got like I within the x direction, j along the y direction, and k unit vector in the z direction, and each unit vector along with other variables is also expressed like that. So the location of r, so this r as an observer RPO for the location r. So r is distance, p is a point, o is the observer. From observer point of view, you will have this particle away as this much from x, as this much from y, and as this much from z. So this is a different way of writing because we involved magnitude and as well as direction. So both things are together. So that's why we have to be careful basically. And of course, when you're following different textbooks, there are different terminologies or different ways of writing such equations basically, where superscripts are used to denote the direction of each component. So this one x, this one is y, this one is z. As in the remainder of the text, I, j, k are used to designate unit vectors in the direction of x-axis, y-axis, and z-axis respectively. So there is another example, very simple example. So what is it? The path of a moving point is defined by the equation. So you got path defined by this equation. So how y and x are related, that's the point here, right? So we are asked to find the position difference from point P to Q on the path where RP is 4, RQ is 3, minus 3 basically. So again, try to understand question. the path is moving, path of a moving point is defined by equation. So there is a some path, let's say it's a random path the curve is making with this equation, for example. You want to find position difference between point P and Q. Let's say we have point P here, we have point Q here. We want to find out what's the difference from P to Q on the path where Rpx is equal to 4 and Rqx is minus 3. So here you have Rp value, here you have Rq value basically. So within this one, what you do, so you have the y component. So the y component of the two vectors can be written as, so we got Rp y is equal to, when you have Rpx as 4, so you see we have the location of Rpx and Rqx. So P and Q are two different positions. As I said, P is this one, Q is this one. So we have been given X values. So now we want to find out what will be Y values for each one. So when X is equal to 4, we have Y is equal to 4 as well. So we have 4 and 4 for X and Y. Next, we have X is equal to minus 3. You plug this in the same equation because we have this relation, and you work out what will be 3. So we have minus 3 and minus 10 basically. So these are the locations for P, and this is location for Q. Sorry, this is for P and this is for Q. So that's what now we are writing. So Rp is basically 4i plus 4j because both are positive. So x was 4, so this is 4i, and we have j, so y was 4, so this is also like 4j, and then we have rq, so this is minus 3, this is I, so this is the x value, and minus 10 which we have calculated from there, so that's the y value. So the position difference from point P to Q. So now we want to find out RQP. So from P to Q is written as QP. So that's the distance from Q to P, P to Q basically. So you just subtract. So RQ minus RP. So RQ is which is minus 3. So I to I actually you subtract, and J to J, because each coordinate is being differentiate basically with the respective values. So minus 3 minus 4, so it will be minus 7, and minus 10 into minus 4 is a minus 14. So now finding the magnitude is simple, basically, which is like 7 square plus 14 square. You can find out the under root, and then that's 15.65 is that value. And the angle actually. Normally in mechanics the angle is being taken as a from positive x-axis, so this is a positive direction. When it says this minus 116.6, so you need to basically evaluate. So how you do this evaluation? First of all, if I locate where this point is basically, so what you do, you have a Cartesian coordinate system, and because x is minus 7, so we are on minus x, so we are somewhere here, and then we got minus 14, so this is also negative, so we are minus 14y somewhere here, so basically we are here some point, and then it is this r basically, so this rqp, yeah, so this r. Now you can work out what is this angle actually. Very simple, because what you can do, either you can work out this angle or this angle, it's up to you. So this angle is basically tan of this height over base, so it's a 14 over 7, so this is tan inverse basically. I'm just solving this triangle, little triangle. So once I know this angle, so then I can find out what will be this angle, right? Because you always represent angle with the positive x-axis. If you go this way, this is positive angle will be reported. For example, there are two ways now. If I know this angle, what I can do,
I can represent this one 180 plus this one will be my angle, basically that will show. The other way is I can go this way, 180 minus this angle, this, but I will need to write negative, so that's why this is written as a negative, right? So you just cross check yourself, you will see that this angle is being shown from here to this one, this vector basically. Yeah. All right, so then we have another problem, 2.2, which was quite similar. So that's why I just, for your practice, I just given here. So what it said, find the position difference from point P, point Q on the curve from y is equal to x square plus x minus 16, and where RP is 2 and RQ is 4. We do similar thing actually. What we do, so we have been given RPX, so x values are given for P and Q. So when x is given, so I want to find out y, which I can find out by using this equation. So RPY when x is equal to 2, so we have x2, so I find y, so I just plug in the value of x. So 2 square plus 2 minus 16, so I have minus 10. So my vector is basically this one at this particular condition, so this one, right? So the next one, when x is equal to 4, because this is the 4 this given, so x is equal to 4, I use same equation and plug as a 4. So when I plug in 4, so I have 4, so that's the vector. So this vector is basically representing the location for this particular value of q basically. So now it's straight away, so you find RPQ basically RP minus Qs. Just make sure you use the right terminology. So he's saying the position difference from P to Q. So you use PQ basically. Yeah, so this solution is using the distance position difference. So you can just use any, so you can use RP minus RQ. And of course, if you use Q minus P, it will be a little bit different. Yeah, so if you just able to mention what terminology are using, then it should be fine basically. So now you can think of RP minus RQ. So we have 2 minus 4, you have minus 2, minus 10 minus 4 is a minus 14. So you work out what's the magnitude, again the same way. So you have 2 square, so of course minus 2 square plus minus 14 square, and you got basically the under root, and that will be 14.14. And the angle is same way you determine, uh, which is like minus 98.1 degree. So it will be same way. So you do physically, this is plotted here, for example. So P to Q. So this is point P. How you mark this point P? From here. How you do that? 2 is positive. So that's the 2. That is the 2. And minus 10. So this is 10 minus 10 because this is negative y-axis. So it's a minus 10. And then the Q point is RQ is basically 4 and 4. So here we got x as a 4 and y as a 4 as well. So that's what location. So basically again, so this is the equation for parabola, y is equal to x square plus x minus 16. So that's how is a parabola. So this particle is moving in a parabola form like that, for example. But we are just want to find out the difference, the position difference when we have RP is a 2 and RQ is a 4 basically. So from here to here we want to find out difference. So this is like one segment of the whole curve we want to analyze. And once you have this one, you can find out the magnitude. That's the difference. That's the difference, 14.14. And you can work out the angle as well. So I'm quite sure when you will do this analysis, so tan inverse 14 over 2. So you need to see if, let's say, you have this angle. So then, so whatever this angle is there, so this angle should be 180 minus this particular angle. So that's why this is minus 98 is provided. All right, so then we have two assigned problem. It's from same chapter, chapter 2, Theory of Machine by Sigley. So I'm just leaving those for you to attempt, but they are same actually. So they are same, they are even simpler. So basically you got like y equation and rpx and rq, and same way the second for the fourth problem is uh, equation, and then you have rp and rpx and rpx minus 3 basically. What is the displacement of the point if the motion begins at? All right, so we need to work out what's the location, what is the displacement, how much it has covered basically. If you start with rpx is equal to 0 and rpx 3 basically. All right, okay, so then we have graphic posture analysis. So again, there will be some fundamental concept over here. So what is this? When the paths of a point in moving link uh, in the moving link of a mechanism lie in a single plane or in a parallel plane, the mechanism is called planar mechanism. We have done this definition already. So if something is moving in one plane, some mechanism or combination of mechanism, combination of links are moving in one plane, that's called as a planar mechanism. So most of our analysis in this chapter as well, we will do planar mechanism. So if it's not like a three-dimensional analysis, because it gets even complicated. So since a substantial portion of okay, so this is like continuation. So this paragraph actually says uh, because mechanism could be in three-dimensional, but we are restricting our analysis for the planar motions actually for the graphic posture analysis. This one. So for first, let us briefly review the graphic process of vector addition. So I'm sure you know this vector addition method. So any two known vectors a and b can be added graphically as shown in figure 2.10a. So this one, for example, you got vector a, you got vector b, and you want to find out addition. What you do? After a scale is chosen, the vector are drawn tie up to tail, tip to tail. So what you do, you want to find out a plus b. What you do, you have two options. One option, you bring this vector b here. So you plot here. So you move this vector basically. You move this vector b to this the tail of the. So this is b, and then head to tail method a plus b. I'm quite sure you have done this one in your intermediate level or some elementary mathematics during your mechanical engineering. So you can find. Or the second option is basically you can move a vector over here. So you can move a vector over here basically. So there are different methods actually you can adopt, but in any case you will have same. So that's why a plus b or b plus a, they are same. But the subtraction is different. So the subtraction is like that. So you got, for example, c vector. So this is a c vector, and you want to do, you want to subtract b from it basically. So what you do, you have the c vector which is plotted here like that. So this is same, this is a parallel vector, and then you have a b, you plot, now it's a head to tail, instead we just bring two heads together like that. So the joining vector will give you, this one will give you the difference. So a will be a c minus b basically. So this is the way. So one more thing is to be careful, you need to do a right scale. So because the scale used here represents the length. So if you have scale, rightly scale chosen, so you will have the length. So basically, for example, this one, what it says, if you have b is this vector, so this vector gives you two things. One, the length of the vector, which is the magnitude of this vector, and one is the direction. So you have to keep both constant. That's why when you measure this length, you will know that what is magnitude immediately, right? And of course, you can also work out what with the angle as well, because yeah, measuring angle through some like compass or anything, you can work out what will be the angle as well. All right, some more nomenclature. So a planar two-dimensional vector equation can be solved for two unknowns. So namely two magnitudes, two directions, or one magnitude and one unknown, one direction. So in a planar problem, if you have any like a mechanism which is like in a plane, the one we are doing here, you can solve that mechanism to find two unknowns, maximum two unknowns. What are those unknowns? They could be either two magnitudes, or you got, if let's say you have been given all magnitudes and one directions, you can work out one direction, or you can have one direction or one magnitude and one direction. So in general, it is desirable to indicate the known with this good sign and unknown with the question mark quantities above each one. For example, this is one of the equation, just made up the equation. So you can write for any four bar link. So because you have four vectors, so it's like a four bar link mechanism. So each vector represents one of the link basically. So within this equation, what is that? So where the first symbol, the good sign, the first symbol represents either this one or this one above each vector indicate the state of its magnitude. For example, here this is magnitude, this is magnitude of vector E, this is magnitude of vector B, this is magnitude of vector C. The second one is basically the 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 second symbol indicates the state of its direction. So this one is a direction, this one is a direction, this one is a direction for E, this is a direction for. So first is a magnitude, second is a direction, right? Yeah, so this is the way you can represent the vector form basically, and we will use this method as well. Another way can also be adopted where like you have C as a magnitude, so the bold vector is represented by direction. So that's why you can write C into C. So this is the direction, this is the unit vector, it's showing direction, and this is the magnitude. So same way for this vector. So D, which is not bold, is a magnitude. D, which is bold, is a vector, there's a direction. And it also has this cap for unit vector. One more thing about this equation, either this C or D. So you see we got 1, 2, 3, 4, 5, 6, 7, 8 parameters, and there are only two unknowns. For example, the C vector, we don't know its magnitude, so that's why question mark is shown here. And we also don't know magnitude for B, so that's why we have question mark. All others are known, so that's why we have a good, the sign of good basically. So either of equation C or D clearly identifies the unknowns and indicate whether a solution is possible. The equation C, vector D and E are completely defined and can be replaced by their sum. So you see, within this one, these two vectors are the one which are completely defined. So D and E, where we have both magnitude and as well as direction. So you can add, like this is addition, so you can add together and represent as a one of the vector, right? D and E. So if you combine D and E, if you add together, let's say they are making a vector A. So now you plug this A instead of D and E. So instead of D and E, I can plug A. So A plus B. So now I will left with C is equal to A plus B. So that's what you have C here. So we have reduced your equation from 4 vectors to 3 vectors now, basically. C is equal to A plus B. Note that any planar vector equation, if it is solvable, can be reduced to a 3-term equation with 2 unknown. So whenever you have some mechanism for a planar vector equations, if it is solvable, because if let's say you have many unknowns, you cannot solve it. This can be reduced to this form. So you got this form basically to a 3-term equation with 2 unknown. Within this equation, we have 2 unknown. Here we had one of the question mark with the magnitude with the C, and this was good. So this is magnitude and direction not known. and this was the magnitude was unknown, and this is, so you see we have one another equation where you have just two unknowns. Depending on the forms of two unknown, four distinct cases occur. These cases and the corresponding unknowns are presented in table 2.2. So we have a table, there are four different options. We will show the solution of these four cases graphically. So we try to find the solution graphically for those individual cases. Yeah, so that's the basically the possible planar vector equations. So we have cases, different cases. So case one, where c and theta c are unknown. Case two, when a and theta b is unknown. Case three, when a and b, the magnitude is unknown. Four is theta a, theta b, the direction. So when we say theta, it means the direction. Letter means its magnitude. And they are further being discussed in equation figure 2.1, 2.11, 2.12, 2.13, and equations subsequently as well. So we will discuss each individual case individually, starting with case 1, 2, 3, and 4. So we will continue with this one with in our next lecture, because it will take some time and it will be good to have continuation when we are solving these ones basically. Thank you.